All righty. Well, let's go ahead and get started. Welcome, everybody. So this is our March meeting of NMSR, New Mexicans for Science and Reason. I'm Dave Thomas, the president. With us is John Covan, our hardworking vice president. I've got several of the crew. Glad to see everybody. So looks like next month we'll have a talk by Mostafa Hassanalian about his work with drones. He makes drones that look like birds, and they mimic flying, and they can fly along with the birds and spy on them. And I think that's a great idea, spying on birds, because who knows? You saw that Hitchcock movie. I think that would be beneficial. So, any comments before we get rolling? I had some prepared slides. I don't see any other. Okay, hang on. Oh, there's somebody. I don't know if you're hearing beepings, but that is people joining. Okay. Okay, now I'm just trying to work my way over to PowerPoint. Slide. And then, okay. Okay. I'm not, okay, here we are. There we are. Got a little lost in the intricacies of Zoom. Optimized for video clip. Well, guess we'll try it. Okay. Okay. Not now. Holy cow. Okay. Well, can everybody see something that says NMSR meeting March 8th?
Yep.
Okay, great. So yeah, we're going to start out by recognizing some of the many efforts of our ailing former president, John Geohegan. And then we'll look at Dr. Hamdoon Khan's $20,000 challenge to Einstein's special theory of relativity. And for that, I am going to show you parts of the challenge. But for the most part, I'm going to just give you my understanding of how these paradoxes in relativity are resolved, and how weird things would be if Einstein was wrong, and things did take on, the speed of light did take on effects from the source or the observer. So we've got some fun little movies coming up. So what is up with John Geohegan? His health has taken a pretty hard downturn, and so he's at a hospice facility, the Village in Alameda, and John and I and Kim got to visit him a couple weeks ago. So, but he's spending most of his time asleep. He wakes up every once in a while, has a sip of soup. So he probably won't be around much longer at all. So if you do want to visit, I'll get you in contact with Janet to arrange something. You can always send a letter, and there's the address on Horizon Boulevard in Albuquerque. And those letters are good, not just for John, who might have trouble reading them, but for Janet and the family members and whatnot. So So I looked back through our stuff. John's founded NMSR back in um, uh, early 90s, late 80s, around 87 or so. And we've got some really neat documents about those early days. Here is John interacting at one of our public events. I think this was a cosmic carnival, and we would bring science demos and the wacky magnet and whatnot to entertain the kids. And he is a great explainer. Oh, here is John doing the bead trick, where you have a string of beads in a cup, and as they fall, the beads sort of rise above the cup. The turning point where the beads are falling actually lifts above the edge of the cup. It's really a great effect, and John was demonstrating that for the public. Magic with a moral. He was a proficient magician, did all sorts of clever tricks, but usually he would make sure that you knew that people like Uri Geller that claimed to be able to bend spoons with their fingers aren't really that special. So John is a naturalist and scientist, liked the great outdoors and hiking around and explaining science. Here he is talking about the intricacies of DNA, probably for one of our encounters with the school board or perhaps the creationists. John is a skeptic, and he helped advance even some experiments. We had a 9/11 truther that came through New Mexico and said there was no way that the top part of a stable structure could fall down and break similar parts below it with a gravitational collapse. And so John made a sort of a model of one of the twin towers. It's got a central core. These lifting weights represent floors. They were connected to the core, as it were, by toothpicks to represent the huge staples that they used in the actual towers. And basically, once one of these floors starts moving, it's going to exert forces much greater than the designers ever anticipated. And it's going to snap these toothpicks here, and the whole thing's going to snap those and those. And we've got it on video. So let me bring that up. And okay, I'm going to have to minimize that. It's a little hard to find things with Zoom. Okay, so we are going to here we are. And let me biggen that for you. There we go. I think this is a silent movie. This is one of the old ones. We had color, but they were still silent. And there's Eddie Jacobs and Jerry Shelton. Bam. Total collapse. Well, there was a $10,000 prize offered for that if we could prove this 9/11 truther fellow from Europe, Anders Bjorkman. If we could just prove him wrong. And okay, so let me get back to PowerPoint. Okay, all righty. So, and John was a passionate teacher. He would really like puzzles of all kinds and algorithms and neat math. And so one time, I think back in maybe 8 years ago, he showed us Euclid's algorithm to reduce fractions. And so I found this in an old newsletter. Let's say you want to divide or simplify this fraction 1071 divided by 462. So what do? You find all the factors of 1071, and here they turn out to be 3, 3, 7, and 17. But it could have had factors much larger. Let's see. Admit. There we got somebody. Okay. Welcome, Kurt. So you would have to feasibly divide 1071 by numbers, perhaps all the way up to almost over 500, just to make sure or to find all the factors. And similarly with 462, obviously divisible by 2, but you'd have to work at it for a while to find 7 and 11 in there. But eventually, once you find all the factors, you can divide out the ones in common, 3 and 7 on top and on bottom, and then your simplified result is 51 over 22. So John showed us Euclid's algorithm, which you don't have to know that 17 goes into it. You compute it. Basically, you start with your big number, 1071, and your number under, you figure out how many times does 462 go into 1071, as is suggested by the fraction. And you don't really care how many times. What you really care about is the remainder. So you figure out that remainder, and then that becomes a new sort of bottom number, and 462, the former bottom, becomes the top. So now we're looking at 462 over 147. 147 goes in 3 times. The remainder is 21. So now we're looking at 147 and 21. And 21 goes into 147 7 times. And what do you know? No remainder. And when that happens, whatever number, that last number that you figured out, that is the common divisor, 21, and 3 times 7. So then you just take this number that you learned from the algorithm, divide top and bottom by it, and it'll divide evenly, and you get 51 over here and 22 over there. Done. Bam. And it works with any fractions, even if they're hideously long. So great little algorithm there. And John, one of his special topics was the special theory of relativity. And he and I wrote some articles to celebrate the 100th year of after Einstein's 1905 papers back in 2005. And it's a neat, really concise little article. And it's still online. There's the address at Skeptical Inquirer. So let's move right on to the challenge. And oh, we've got some more people waiting. Okay. Welcome, Bill. Righty. In fact, I'm going to, well, we'll just keep checking that. Okay. All righty. So, in my email the other day, I found an email from Dr. Hamdoon Khan, who has written a paper on relativity, and he has pledged a reward of $20,000 to anyone who can disprove his supposed rebuttal, his disproof of special relativity. Here he is. Here's his paper. And here's the address. I think if you just search for this title, The Ultimate Sophistication of Special Theory of Relativity, and slap in Hamdoon Khan, you'll find it. It's out there, findable on the internet, and quite a few views. And he's got a couple of YouTube videos. And, yes, question? Or I heard maybe a question. Okay, well, so we've got a couple short videos, and then we'll just jump right in. I think they're pretty hard to watch. There is so I'm going to include the subtitles, but I think let's just watch the second one, which goes into these paradoxes, and then leads up to to the challenge. So we'll just pop right over there. Yeah. Okay. Let me just copy that down. Copy. Alrighty. This video isn't available anymore. Holy cow. Maybe he's withdrawn the challenge. Well, normally, this would be the time when you'd go, oh, crap. I don't have the challenge anymore. But as soon as I got this video or this letter email from him, I said, you know what? I'm going to save that video because, you know, you erase stuff off of YouTube. It's so transient. But so we have videos.
Dave?
Yes.
It looks like there's a box around the URL and it looks like you missed the last letter.
Oh, so maybe it's still there because I really would want to get his subtitles. So let's go back to oh shoot, I missed the A on the end. Thanks. Okay. And it's always something. So let's get back to Safari, YouTube. Okay, come on. Now Zoom's getting in the way. Oh. All right. And I type in an A. And oh, here we go. Okay. All right, he didn't erase. The challenge is still on. Oh, let me get it louder.
In this video, we are going to talk about my own 4 different paradoxes of special relativity, as I talked about them in my last video. So let's get started. I have 2 balls in my hands, A and this one is B. A is suspended in the air and B is moving at a constant velocity towards A. As B hits A goes backward. But when we take special relativity into consideration, based on that, B can claim that I was at rest and A is the one that was moving towards me. So as I was hit by A, I should have been gone backward. Now the question is, which ball went backward? Is that A or B? And which was in motion, B or A? I have 2 magic sticks in my hand, Alpha and Bravo. Both the sticks have the width of 2 centimeters. The speciality of these sticks is no force in this universe can break them apart as long as the width of these sticks is exactly 2 centimeters. But if the width of either of these sticks becomes less than 2 centimeters, then that stick can be broken by another stick which is in its perfect size. Now, a modern physicist comes into the picture. He claims that he can break one of the sticks using other one. And he sets both the sticks at a distance and lets Bravo travel towards Alpha at a constant velocity. As Bravo hits Alpha, Bravo becomes broken. Because we know, based on relativity, the width or the length will be contracted in the direction of motion. But here's another problem. Bravo claims, wait, why am I broken? Because based on relativity, I can claim that I was at rest and Alpha was moving towards me. So the length of Alpha was contracted, which means the width of Alpha was contracted. So as it hits me, Alpha should have been broken by me because I was in perfect condition. Now the question is, which stick was broken by which? Two friends Alex and Bob were living in a fantasy universe. The distance between their planets is 12 light years. All inhabitants in their planet or the universe only dies as they complete the age of 40. When both these friends were at the age of 28, Bob decided to meet his friend Alex. So he started to travel towards his planet at 12:13 the speed of light. When we do the math for this, according to Alex, it would take 13 years to Bob in order to reach his planet. That means to say, Alex would be at the age of 41 and Bob at 33. In other words, Alex would have been dead by then, as he already completed the age of 40. But according to relativity, Bob can claim that he was at rest and Alex is the one who was in motion towards his planet. Based on that, Alex would have been alive and Bob dead. Now the question is, who is alive and who is dead? Imagine that there is a magic cage that has the mass of 10 kilograms and it always travels at a constant velocity of 0.6 the speed of light. The interesting thing about the cage is when its relativistic mass hits 199 kilograms, it will teleport from our Milky Way galaxy to somewhere else. But strictly, only human can enter the cage. No animals or anything else can be taken with. The people of the place who had the maximum mass of 130 kilograms entered the cage and tried to hit that required relativistic mass. Unfortunately, none of them could succeed. Therefore, they couldn't experience the teleportation in their lifetime. One day, a wise man came to know about this cage and its rules. He claimed that he can make it happen. Let the teleportation take place right in front of their eyes. Everybody started to laugh at him because he had the mass of only 110 kilograms. Even those who were heavier than him could not succeed. The man didn't say anything to him, simply took his son who had the mass of 40 kilograms along with him inside the cage, because there was no restriction on how many people could enter the cage at once. There you go. Once they enter the cage, the relativistic
I saw the
mass
last part of the
became
game.
199.84 kilograms.
Yeah.
Wow. They hit the target and got teleported. But wait,
Possible.
the man and his son climbed that they
got
were
it
not
down
teleported
here.
because once they enter the
Yeah, we
cage,
can do
they
it on
were
the
at
TV.
rest. And the total mass of the cage was only 160 kilograms, therefore no teleportation could take place. Now the question is, who is right? Were they teleported or not? These are my 4 paradoxes of special relativity. So let's see if any of you can prove them wrong and win $20,000 prize amount as I announced in my last video.
This is not just a deck of cards. This is a collection.
Alrighty. Wow. So that was pretty wild. And he had some pretty amazing challenges, like this magic container that teleports to another galaxy. Wow, that's something. Okay. So so you can find these if you search on YouTube. But there's the addresses, and I think really I like the second one a little better. So let's talk about that first challenge, and this is from his paper, the technical paper, and basically he's just describing a sort of Galilean experiment. It's not even, you don't need relativity for the thing that he's suggesting. So if you have two equal masses,
Okay, I thought I'd show a few more things. You
and
do a pair of
give
bowling balls.
one
You've
some
got
momentum
equal
into the other,
mass,
they can transfer momentum
bowling
completely if the masses are equal
balls.com. This
and
search
if it's an
online. You
elastic
can find them at
collision.
bowling alley,
So this is a great
garage
little
sales,
demo here.
stores, etc. But it does help to have ones that are really close to the same make and mass, and they're pretty elastic as far as collisions. And so we already showed this one. So if I pull one back and let go, it
Perfect.
stops, and the other one goes out with about the same speed
Perfect transfer.
because it reaches about the same height. And
So it's a great little video. He goes into some neater experiments. What happens when both balls have a little velocity, for instance. But you know, basically, and if you have two equal mass pool balls on a table, and one's at rest, and then you have a nice head-on collision with the other one, not a glancing blow, but middle to middle, then the striking ball, the cue ball, will stop dead, and the ball that was hit will take up all that momentum, and it makes a straight line. So this is the type of collision that we're going to look at. And so I made this diagram, and I have sent it to Dr. Khan. I have not heard back. And I sent it with an explanation, but basically, here are 3 points of view of, say, a pool table experiment where we have a lab reference, or you could call it the pool table reference frame. And in this top picture, that is the pool table right there, this rectangular thing. Ball A is motionless, and ball B is moving toward it at speed V, and this is before the collision. And then after the collision on the right, then the lab will still be motionless. The pool table in the pool table reference frame will be motionless, and B will be the motionless ball, and A will be moving off at the original speed V. Basically, momentum is transferred from ball B to ball A, just like we saw in that video just now, which were in the classroom reference frame. But now, if you want to think of this relativistically, how is it different for A in A's reference frame as opposed to B in B's reference frame? So here is the point of view of A, and since A is initially at rest before the collision, this picture of A at rest and B advancing toward him at speed V, that's the same as the lab reference frame. But what's different is after, then A, because this is A's reference frame, A still has velocity 0. And so what A notices is this ball B was coming toward me, and then bam, it hit me, and now this ball B is moving away from me, and the whole lab is moving in the same direction as that ball. Funny that. Now let's look at the exact same collision from B's reference frame. In B's reference frame, he's at velocity 0, and A is moving toward B at velocity V, and the whole lab, the pool table, as it were, is moving toward B at that same velocity as A. And then B sees A smack him, and then B is still motionless after the collision because it's B's reference frame. And so B sees A coming toward him, and then B sees A going away from him, and B notices that now B is at rest with the lab. The lab isn't moving anymore. The lab was moving toward B over here, and it's at rest over here. So you'll notice that where the first part of A's reference frame was like the lab reference frame, the last part of B's reference frame is exactly the same as the lab reference frame. So we have perfect symmetry. In the lab reference frame, we see the 2 pool balls doing or just what pendulum balls would do. In A's reference frame, he sees the ball coming and then moving away, and the exact same thing happens in B's, and both A and B observe during the collision that their environment undergoes a velocity change. So it's exactly symmetrical, and I demand the $20,000 now. But let's move along. So the sticks, basically, this is the paradox where, because of length contraction, usually it's with a hole, and you have some hole that perhaps if the one stick was at high velocity, it could fit into the hole, but otherwise it would bang off the hole. And those are really the flaw of those paradox so-called disproofs is they're not taking into account one of the prime components of relativity, and that is that things that are simultaneous in one reference frame are not simultaneous in a reference frame that's moving towards it or away from it at a constant velocity. So the duration of events, it need not be the same in different reference frames. And it's a weird concept, but basically that's exactly what happens. So which stick will be broken by which? Basically, this repeats what he said in the movie. So let's move on to challenge number 3. This is where Alex and Bob, at the same time, he says, when both of them were 28, Bob started to travel at a constant velocity, 12/13 c, towards Alex's planet. And the gamma factor for that is about 13/5, and that's correct. So according to Alex, as Bob is in motion, he would cross this time period. It would take 5 years for Bob because of the relativistic effects. So what Bob would experience is 5 years, Alex would measure as 13 years to travel those 12 light years. And therefore, and then he has some very arbitrary rules that you die when you reach age 40, and then Alex would be dead, but Bob would still be alive. And then here's the paradox, and this is basically just a twin paradox. If you consider this from Bob's point of view, Alex is the one in motion. Alex should have his time dilated, and Bob should be the one that's dead. So there's that, basically the twin paradox. And number 4 is this incredible container that if it exceeds 199 kilograms, poof, it magically teleports to Andromeda. And so it's just not a realistic sort of thought experiment. I mean, if you want to construct a thought experiment to challenge relativity, don't bring this magic stuff that will never happen. It's just a huge distraction. So, and he's got some math errors. He says that this factor, that the mass of the 120 plus the 10 kilograms, 130, should be multiplied by 1.249 to get the relativistic mass. But he's got a velocity of 0.6 c, and the gamma factor for that is 5/4, 1.25. So that's math error. I mean, that's an arithmetic error. And there's more. So basically, he says the mass should have gone over 199. Actually, should have gone to 200 if he had just used the correct the gamma factor of 5/4. He would have got 200. It still would have been a ridiculous and not very applicable example. So here's some responses. And so number 1, I explained that. It's really explained by Galilean relativity. Doesn't require, or Galilean kinematics, if you wish, doesn't require a special relativity at all. Number 2, if the sticks have a finite width, you have to consider the separate times at which front and back sides of the sticks collide. Events which are simultaneous in one reference frame need not be simultaneous in another, and the paradox usually vanishes. Number 3, the error is assuming both Alex and Bob were exactly 28 at the exact same absolute time when they were separated by 12 light years. That's a stipulation of the problem, but Alex and Bob are in relative motion. Events in Alex's frame are not simultaneous with those in Bob's frame. And really the only point of simultaneity when you can say, yep, this is the same point in space-time is when they meet, when Alex meets Bob at the end of the journey. That you can hang a handle on. So the effects of time dilation, length contraction, mass increase only happen in moving frames. They do not happen in your own rest frame. And John and I had a big argument with a relativity skeptic. Wilson was his name, and he would really confuse. He'd think length contraction should happen to you. That if you were Captain Kirk in your starship and you were going super fast, that the painting on the wall of the Enterprise should shrink in the direction of motion. No, no, no. When Captain Kirk is in the Enterprise, even if they're going almost the speed of light, let's not talk about warp now. Everybody's going to look the correct width. The paintings are going to be the right width. It's only if you look at another spaceship that's zooming by you at some good fraction of the speed of light, their paintings will look shrunk. But that's actually a pretty hard experiment. In fact, an incredibly hard experiment. So, so this thought experiment about the magic teleportation just doesn't disprove relativity for me. So what is involved? What is the simultaneity of time? What is time? That's something that Einstein redefined. How are these relativistic paradoxes resolved? And I'm going to lead up especially to the twin paradox. Which twin is older, the traveler or the stay-at-home? So any comments before we jump into a proper discussion of relativity? Oh, all righty. Well, it looks like we're still zooming.
Dave,
Yes.
one thing about the minor, relatively minor arithmetic, he may have been doing that with a slide rule. So, you know, getting a little fluctuation in the third significant figure is about.
That's a possibility. I grew up. All right, my first semesters in college were with the slide rule.
Me too.
Yeah.
I predate you too.
Yeah, indeed. Okay. Any other? That was a good comment. Any others? No. All righty. Well, if you feel you know, something relevant, just chime right in, because we're just having fun here. So basically, this is adapted from my class lecture that I give on relativity. Special relativity is based on two principles. It's really one principle, but for now, these two are: one, laws of physics are the same in all inertial reference frames, and two, the speed of light is independent of motions of either the source or the observer. And so those are the axioms. This first one, I like to use the analogy of, say, a kid with a soccer ball on a train and an inertial reference frame. It's like cruise control on steroids. You're going at a constant velocity. You're not turning left or right or up or down. You're not speeding up or slowing down. It's just straight linear motion, and like a train would do. But here the train is stationary, stopped. We have a young lad in there with a soccer ball. He bounces it, and there's a hole in the ceiling. Thank goodness, or else it would have really just come down on him hard. And the ball goes up and it slows down according to the laws of physics, and then it falls back down, and he does it again. So there's the law of physics that governs this, F equals ma, with vectors. In this particular instance, the solution of the laws of physics, the answer of physics, is that the position is given by this equation, which describes how the ball goes slower and slower and peaks out and then falls back down, gaining velocity. So now let's have the same kid, the same train, but it's moving at a speed v. And so now we see the ball have a parabolic trajectory. And when it lands, well, the boy has moved to catch up to the ball. The whole train has moved. So, but basically now the ball and the boy and the train have a sideways motion, exact same law of physics. But now the result is, well, the y part is the same, but now we have a new x part for this particular reference frame and situation. Now we've got an x velocity to think about. So the laws of physics are the same in both situations. The results might depend on the reference frame. So here's that second axiom, as it were. Light speed does not depend on motion of source or observer. Ordinary objects are not like that at all. So I like this analogy of the same old train and the same kid, same soccer ball, but now he's kicking it and bouncing it off the wall of this tunnel that the train is standing right in front of. And what happens when you bounce a ball at a certain speed off a tunnel? It's going to rebound a certain distance. And there we have it. That's a result in this reference frame. If we redo the experiment, where now the young man is speeding, the train is speeding into the tunnel. So now the ball would have not only the speed that the lad gave it, the original speed of the ball, but it would take on the train speed too. And when it hit that tunnel, if this train was going fast enough, that ball would rebound much farther. And this is what happens with real objects. But if instead of a bowling ball, the young man had a flashlight and he turned the flashlight on, in the first instance where the train is at rest with the tunnel, nobody would argue that those photons are going to hit the tunnel at the speed of light. But the weird thing about relativity is, in the second instance, let's say the speed of the train was 90% of the speed of light, and then the kid turns on the flashlight and those photons have that speed of the train as they are launched. Wouldn't those photons hit the tunnel wall at 1.9 times the speed of light? And the answer is no. They would hit at the speed of light. Doesn't depend if the train's going forward, backward, or motionless. Even if the train is going 99.99% of the speed of light itself, when those photons hit the tunnel, they're going to be going the speed of light. So, and now I'm going to demo that really that second principle of speed of light doesn't depend on source or observer follows from the first principle, namely the laws of physics are the same in all reference frames. And for this, and this is really as much as Michelson-Morley experiment, this is what got Einstein into relativity, was trying to figure out Maxwell's equations and what happened with the speed of these waves. And this was at a time when, before Maxwell anyway, we didn't know that what the medium of electromagnetic waves was. And in fact, the Michelson-Morley experiment was trying to look for some ether that those waves were propagated at. But basically what Maxwell's laws show, when you take the vector form of the laws and do some curls and combine results, you get what's called a wave equation. And the speed for those waves comes out to 1 over the square root of the magnetic constant times the dielectric constant. And these are things you can measure in a lab. This is a capacitor experiment. That's a magnet experiment. And you get the speed of light. So basically, there's nothing in these equations that says, oh yeah, the speed changes if your source is moving, or if you're moving as you measure them. If these light waves are propagating through space, they're traveling at this speed. And it's pretty much an amazing little thing to think about. So here I've got a little movie that I made with Python, and it shows like electrons in an antenna. And as they go up and down, they make waves which spread to right and left. And the thing that I'm trying to demonstrate here is that this frequency and then half of that frequency, the waves are still going at the speed of light, c. The wavelength is twice as big for the half of the frequency, because frequency times wavelength, that's a constant. But the speed of the light actually is that constant, the wavelength times the frequency. So there it is for same frequency as before on top, double the frequency now on bottom. The bottom antenna is going twice as fast, generating waves of half the wavelength, twice the frequency, but exactly the same speed of light here, speed of light there. It doesn't depend on the frequency. It just depends on speed of light. So here I've got one going at a 45-degree angle, just to demonstrate that you don't get waves in the direction of radiation, only perpendicular to that. But the important thing here, those speed of these waves, exactly the same as the speed of the waves on top. Once launched, the wave goes at speed c, and it really doesn't, your source could change from going up and down to left and right, and yeah, new waves would come out, but they'd all be going at the speed of light, c. So this one shows on the bottom, it's doing its original frequency, but now the antenna itself is moving toward the right at half the speed of light. And just like before, it creates electromagnetic waves, which once they're created, they don't know their source is moving. They're going through space at their speed, c, 1/square root of mu naught epsilon naught. And it's the same speed. The waves in front are bunched up. You get sort of a Doppler shortening, and the waves in back are spread out. And that's just like the Doppler effect. But the speed of the waves, even though the source is moving, the speed of the waves is c. This is a result of the laws of physics. And what if the source was fixed and the observer were moving? It would really be the same situation. So these the waves, as they hit you, would be clocking at the speed of light. So the laws of physics, specifically Maxwell's equations, say that EM waves travel at a speed c, 299,792,458 meters per second in a vacuum. Doesn't matter of the speed of the source or the observer. And just one assumption, the laws of physics are the same in all reference frames is needed. And I should add that general relativity, it's not inertial reference frames, it's any old reference frame, even a rotating reference frame or one that has mass. So consequences, we've got time dilation. Events take longer in reference frames that seem to be moving. You got your length contraction, and you've got mass momentum increase, and the inability to accelerate anything, even the tiniest electron with a wonderful electric charge that we can push it around with. We can't get it to exceed the speed of light because that energy that we try to put into speed manifests as mass instead. E equals mc squared is one of the results of special relativity. So the big thing that really I think is still the reason for resistance to relativity is that Einstein redefined time, and time is not absolute. There is no absolute clock in the universe that everybody compares to. Every reference frame has its own clock, basically. But there is an inseparable connection between the speed of light and time. So this is from Einstein's book, where he tried to describe this thought experiment about a train. He's got a train on an embankment, and train's going a certain speed, and then you got some lightning things. So I've made a little video to illustrate this, because this is really what shows you that things are not simultaneous in different reference frames. Here come two lightning strikes. Those are simultaneous at A and B, and this fellow M is right between A and B, motionless. And so in this reference frame, M, the middle guy, is going to say, dun, 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 dun. Whoa, look at that lightning in front of me and behind me at exactly the same instant. He is going to agree that these lightning strikes were simultaneous. But now let's look what happens to somebody moving at, when the train's moving at, say, a third the speed of light. In the reference frame, they're simultaneous, but the train sees B's lightning first and then A's. And then this effect is even bigger for half the speed of light. Engineers goes, whoa, lightning at B. Well, that was really cool. I saw lightning in front of me, and whoa, now there's lightning behind me at A. So I hope you can see that these, what are simultaneous in the rest frame are not simultaneous to the train moving at a constant velocity. And if those events aren't simultaneous, then things like time differences are no longer necessarily equal. So John and I, in that Skeptical Inquirer article, we sort of worked up some examples to show why the Lorentz transform should work, should be valid, but without going through a really complicated derivation. So I'd like to try that for you. But it requires two simple concepts. One simple concept is just radar ranging. You emit a pulse, it goes through space, bounces off something, comes back at the same speed, and you measure the total elapsed time, and you divide that by 2, and that's the and then you multiply by the speed of the pulse to get the distance to the pulse. So I tell my students, I could send a grad student to Albuquerque, and I'll say, go to the limit, 75 miles an hour, and they'll come back. If they come back in 2 hours with the pencils or whatever I told them to get, then I could take that time, 2 hours divided by 2, 1 hour at 75 miles an hour is 75 miles. This place called Albuquerque must be 75 miles north of me. And that's all really that these radar ranges are. If something is 3 light years away, it'll be 6 years between the sending out of the signal and the receiving back of the signal. If the object is 6 light years away, then there's 12 years between when you send your signal and when you get your answer. So let's take a little trip. So I've got some little Python movies that I made for this that show a space station, A, that's the stay at home, and B is going to be our zippy little traveler that has a neat spaceship that can go right up to the speed, almost the speed of light. And but here, B is going to be going 60% of light speed, and A is going to shoot off a light at 6 years. Bam, 6 years. It bounces off about 15, and it returns about 24. 6 years, about 15, about 24 to go back. And it's hard to see what's happening here. So what if we added a vertical axis of time? And I've done that here, and bam, at 6 years, the light ray sends out. You can see the light ray has a little different path than the spaceship, bounces off at 15 years, gets back to the space station at 24 years. So by spreading out the vertical axis of time, we get this neat diagram that shows space going this way, time going that way. And from, all I have to know is the thing left at 6 years and it came back at 24. Just those two numbers tell me that the difference between those, 18 divided by 2 is 9. It bounced off 9 light years away. That's my distance. And when did that happen? 24 plus 6 divided by 2 is 30, divided by 2 is 15. It happened 9 years after the pulse went out at 6 and 9 years before the pulse came back at 24. 9 years on either side. So, but at a time 15 years. So you get not only distance, but time. And on these diagrams, light has a slope of 1, but because it's distance, not time on the horizontal, the slower velocity is actually a steeper slope. The ship has a slightly, and I would love to take credit for these diagrams. I certainly didn't invent them. It turned out Einstein's professor, Herr Minkowski, came up with them, and they are called Minkowski space-time diagrams. And yes, these are the ones where these yellow regions are in the past. These are things that could affect you, and these are things that you may affect, but things that are outside your light cone, you're not affecting them. There's no way you could reach them at the speed of light before they were gone. So let's look at 2 pulses, boom, boom, and 2 reflections and 2 returns. And now this one's really hard. Pulse is 2 years apart, and then they bounce off at different times. So let's spread that one out. Oh, I think I may have, yeah, John Durr. Okay, all righty. So, oh, there's some, okay, I think that was just John Dingen. All righty. So here we have 2 pulses that leave 2 years apart. At 6 and 8 years, they bounce off at 15 and 20 years, and they return back to the spaceship at 24 years and 32 years. So this first part is just the part we saw before. All we've added is a second beam of light at 8 years, and it's going to come back even later. And so we can figure out both of these points. And so this first bounce happened at 15 years at a distance of 9 light years out. Second bounce, 20 years at a distance of 12 light years out. So they went spaceship B in A's reference frame. A's reckoning, spaceship B goes 3 light years, and it took 5 years from 15 to 20. So he was going 0.6 speed of light. And in fact, this is how radar work. You know, if this was a galactic cop doing this, and the speed limit was 0.5 C, then the space station could issue a traffic ticket to space station B. But the weird thing is that it wouldn't even happen for 12 years after the infraction had been confirmed. So you'd get those tickets much later. So that was simple concept number 1, the radar ranging. Number 2 is if you have things that are separated, and one is putting out constant regular pulses, and you're just looking at the times between those pulses, just like you were having drum beats between tribes out there in the jungles of Africa. And you're just looking at the intervals between the drum beats. When your source A sends the drum beats at regular intervals, and B is retreating, it's going to stretch out the drum beats. It's going to make them take longer. And let's say that B, every drum beat that B gets, they send a signal back towards A. And this could be like a passive radar reflection, just a radar beam bouncing off some spaceship that doesn't want to talk to you. Or it could be a detailed message. Hello, send Aunt Margaret my greetings. We love you. But every message that B gets, because A and B are separating, A's reception of B's new signals are going to be slowed down, and by exactly the same ratio. And so that's the key. If relativity is real, then and you know we're just equally able to think of A moving away from B or B moving away from A, then B's observation of A's delay must equal A's observation of B's delay. And then if the 2 ships are advancing closer together, then these intervals will be reduced. As you send signals and the ship is coming toward you, they're going to come back faster, and they're going to be received faster and come back faster still. So just as A's pings are delayed on arrival, B's responses are delayed a second time by the same ratio. So boom, 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 boom. There's the original reflected, boom, 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 and then the return back to A. So the point I'm trying to make with this reciprocity is, let's look at the color. These first ones are yellow. So the yellow pulses, the time between them, the green pulses is a certain ratio, and the red pulses, red to green, is the same delay as green to yellow. And basically just the basic fact that as things are getting further apart, it takes longer for those waves to bounce off. And so you're going to delay your regular drum beats. So that's it. So where's the reciprocity? So here we just had this neat space-time diagram. And okay. And so from 24 to 8 years to 32, that's a difference of 8 years. And from 15 to 20, that's a difference of 5 years. And from 6 to 8, that's a difference of 2 years. What I'm saying is that the 8 years to the 5 years of that ratio should be exactly the same as 5 years to 2 years. And you may notice, hey, they're not the same. Those ratios are not the same. 8 to 5, that's 1.6. 5 to 2, that's 2.5. They're nowhere near the same. And I said they should be the same. And they, in fact, should be the same, because what we're talking about is not what A is measuring for the time difference between these pings off of B, but what B is measuring. B is the one answering the letter saying, yes, hello to Aunt Myrtle. So why are they different? Because Einstein's train things that are simultaneous in one reference frame, not necessarily in another. The time differences are affected by your speed through your different reference frames. So basically, what we do, and John came up with this all those years ago for the 100th anniversary, was that instead of assuming that this is 5, we just call it X, the unknown. X is what B actually measures between this reception from A and this other reception, which in A's time frame are clearly 5 years apart. So we're just going to call it X, and we're going to demand that 8 to X, the ratio of the final reception to the first bound signals, has to equal X to 2, the ratio of the first bounds to the original signal periods. 8 over X is X over 2. 8 times 2 is 16, equals X squared. X is 4. We've solved for X. So basically, for this to actually work, for relativity to work for these ratios of drum beats, then this time in here, it has to be 4 years, can't be 5 years. And basically, this is a way to show without a huge derivation that this is time dilation. Time dilation is correct if you have the assumptions of special relativity, namely that the speed of light does not change depending on source or observer. And so in this case, time is dilated by 25%, 5 to 4. A and B are both correct in thinking B is zooming along at 0.6 C. But B thinks he's only traveled 2.4 light years. B has been traveling for 4 years. B looks at his odometer, and 4 years at 60% of light speed is only 2.4 light years. And that is where you have length contraction, where A measures time dilation of B's time, B measures length contraction of A's universe. So they're very symmetrical effects. And here is the good old Lorentz transform. Basically, this very same problem reduced to just the Lorentz transform. And sure enough, the delta t comes out to 4 years, 16 minus 12. And in the B's reference frame, those bounces that were 5 and 15 and 20 years rather were 12 and 16. Okay. So if B is traveling toward A, these pulses, then they're going to come in faster. So they're 8 years apart on the initial send out, and they're 2 years apart on the reception. If we just work out the math, 2 to X equals X to 8, and it still comes out as 4 years. So you basically have time dilation, whether the two ships are moving apart or moving together, you get time dilation. One ship measures the other ship's time as dilated. So you have symmetry. If you go faster, here we got some pulses that are 2 years apart, and doesn't say actually what time they're bouncing, but looks like quite an interval between them. Ooh, first interval comes back at 27 years, and the second one's going to come back 45 years. So here's the situation, and if we do the math for this point, we're 15 years of time, 12 light years out. Over here, we're 25 years, 10 years later, 20 light years out. So in 10 years from 15 to 25, we moved 8 light years from 12 to 20. So 8 light years, 10 years, that's 0.8 light speed. So yeah, you get the velocity. Once again, 18 to X equals X to 2. If we solve for that, X squared is going to be 36, X is 6. So what takes 10 years in the space station's reference frame only takes 6 years of the spaceship's time frame. The ratio is 5 to 3, exactly as you would have gotten had you used the Lorentz transform and this famous equation. Length contraction. If Einstein was zipping along in his spaceship at near the speed of light, yeah, he would be contracted in the direction of motion. This would be the hardest thing you could possibly measure, because think of it. Here you are, got your camera ready, and here comes the ship at 99% of the speed of light, and it's gone. I mean, it'd be hard to measure, and you'd have to consider things like, well, when the ship goes here, those photons are going to, take a few nanoseconds to get to you. Really hard experiment. Very hard to measure. But the length contraction that is easy to measure, we just showed it for spaceship B. If we're speeding through some neighborhood, that neighborhood is contracted in the direction of our motion, and that distance is easy. You just look at your odometer and see how far you've gone. And so this is how, if you could go really a high fraction of the speed of light, you could take our Milky Way galaxy 100,000 light years across, and if you were going fast enough, you could shrink it to be 10,000 light years across, and then you could actually get across it in a shorter time. But because of time dilation, the people back home would be dead for hundreds and hundreds of years. So here is that length contraction. 3 light years in the spaceship's reference frame is contracted to 2.4 light years, according to B, who says, yeah, I'm going 0.6 of the speed of light for 4 years. So this is an experiment we have done. And so we've got these cosmic rays like protons that hit our outer atmosphere, and they create muons that are very short-lived, radioactive. They're like electrons on steroids, and they decay usually with a half-life of about 1.5 microseconds, and they're cruising down at 99.95% of the speed of light. So their gamma factor is over 31. So a time of 4 half-lives would be dilated out to over 200 microseconds. And a distance of 60 kilometers, the distance to space, would be contracted by this factor of over 31 to about just under 2 kilometers. So here's how it works. This is classic physics on the left. Here the muons they appear on the edge of space 60 kilometers up. They have a journey of 60 kilometers at the speed of light. That's going to take 200 microseconds. And they have these half-lives of 1.5 microseconds. So that's about 128 half-lives. How many muons hit the ground? 0. You divide even a huge number in half 128 times, and you got nothing. If you have $1 billion and you divide it in half, within 2 months, you'll be penniless. So over here, we've got the muon reference frame. We are the muon. And here, the muon sees this incredible length contraction effect. And the muon sees this 60 kilometers of Earth from space to the ground squeezed into just under 2 kilometers. How long does it take to go 2 kilometers? About 6.3 microseconds, about 4 half-lives, which only 4 half-lives you divide. So you go 50%, 25%, 12%, 6%. You're down to about 6% in 4 half-lives. So you got some muons on the ground, unlike classical physics, where 0 muons hit the ground. So now this third one, we're looking at it from the Earth reference frame. This is 60 kilometers. And yes, that muon has to go that whole 60 kilometers. And at near the speed of light, it takes 200 microseconds. But now we're seeing the time dilation to where what seems like 200 microseconds to us was extremely dilated, only 6.3 microseconds for the muon. So in the Earth reference frame, we see time dilation explain how the muons can last long enough to hit the ground. 6% of them hit the ground. The laws of physics are the same in the muon reference frame as they are in the Earth reference frame. They both come out with the same answer, 6%. But the classic experiment is much different. So for those curious, there is an experiment on this that we've actually done. And there's the reference for a Special Relativity, William Geraint von Rosser. Okay. So how can two observers in relative motion both see length contraction, time dilation in the other? And this is one of the things that our relativity critic was hung up all those years ago. Basically, length contraction, time dilation never occur in your own reference frame. They only occur in reference frames that are moving with respect to you. So if I had a divergent lens, if I looked at you with a divergent lens, you look smaller to me. I would look smaller to you. We would both look smaller. We haven't changed size. I'm the same size. You're the same size. We appear to be smaller. So it's a measurement effect. Now here's a really neat experiment that we actually have data for that shows that Einstein was right. The speed of light does not depend on the motion of source or observer. So, and this is based on a real system, Castor C, a binary system, where we've got two stars basically in a really tight, close, and fast orbit. And so here's the setup. And let me just expand. So we've got three points. A, the light is coming toward the Earth. And if this is where we would measure it, if Einstein's right, we've just got these stars going back and forth. If this light took on the speed of the star, and the star is moving fast toward Earth way down here, then the light from A would arrive early, and it would arrive earlier over here. The light from B, because it's going perpendicular, to our viewpoint, it wouldn't be slowed down at all. B here would be exactly the same B there, but this point C, where this star is moving away from us, its light would be here if Einstein was right, but it would be delayed because this light would be the speed of light minus the speed of the star. C gets delayed, whereas here at A, it's the speed of light plus the speed of star. A comes in early. So you can see this just naturally pushes these two sine waves of the two stars going back and forth. It just folds them over. And this is time running left to right. So actually, Castor, that was for 5 light years away. Castor actually is more than 10 times that distance. And this effect has 10 times the time to make it worse. And it is much worse. So we would have all these sine waves, just beautiful, perfect, vertical, if Einstein was right. But if Einstein was wrong, they would be folded over. And at any single time, you would see 36 stars. So here's the real experiment. And this is from radar. This is not visible light. But here are the two beautiful sine waves, straight and just like Einstein said they would be. And these particular stars orbit in under a day. So that is just like 6 hours or so. And here is the reference for that. J.H. Smith, Introduction to Special Relativity. One of my students said, what would it look like on a telescope? Great question. So I came up with an answer. And here's a movie showing, this is us 5 light years away, looking at these two binary stars, a blue one and a red one. And but we're looking at them from the side. So we just see two pairs of simple harmonic motion. And we see the each star goes from right to left and then left to right. And they cross at maximum speed in the middle, just like you'd expect. And over here, I've got if Einstein was wrong, and the light from those stars took on the speed of the star, the light coming toward Earth would come in faster. The light leaving, going away from Earth would come in slower. And what do we see? We see two stars appear on the left, and they move to the right, and they get farther and farther apart. And then blue stars appear on the left, the red stars different. So if you'll notice, like here's two red stars appearing, and then if you'll notice, this red star is going to annihilate with a different red star, not the one it created with boom. And it just happens again and again. Things go always left to right, never right to left. Totally weird. But this is exactly what would happen. If Einstein was right, we'd see the two stars just going back and forth. But if Einstein was wrong, like at this time, we'd see two blue stars appearing and two orange stars. We'd see the red stars disappearing. And then we'd see the blue stars getting farther apart. And then a different blue star would annihilate, and they would wink out, and new red stars would wink in, and it would all be moving in the same direction. Whoa, that is so weird. And here's what it would look like if Castor C was its actual distance. So if 51 light years away, we would see dozens and dozens and dozens of images, all moving in the same direction, appearing on the right here and disappearing into other images on the left. And wow, there you have it. So, so when I gave a speech to an anti-relativity group that had a convention in Albuquerque, it's one of those philosophical naturalist societies. I said, guys, if you want to disprove Einstein, this is your ticket. Get those telescopes, look at those binary systems. If you can catch stars doing this, you disproved Einstein. Let's go for it, guys. Haven't heard back yet. So this brings us to the big one, the twin paradox, horrible pun. not a twin pair of docks. Sorry, I had to inflict that on you. But what is the twin paradox? Basically, that was one of Hamdoon Khan's things with Alex and Bob. How, Alex would be dead in one reference frame and Bob would be dead in the other. This is the exact same problem, but here I'm going to explain it to you. And it's not a paradox once you've worked through it. So basically, because of time dilation, you've got two twins. One goes out on a journey and back. The twin who left is observed to have a slowing down of time and will end up younger than the twin that stayed behind. But here's the paradox: can't either twin be considered at rest and the other twin moving, who is older? And that's exactly the way Hamdoon derived it. So I've got a thought experiment, and this one has no brothers that die at age 40. It's just travel through space, and we can track everything with space-time diagrams. In fact, we've already looked at these space-time diagrams, but we basically have a traveler, a space station A, and a traveler B. B travels at 0.6 speed of light, and in 15 years, B travels 9 light years away. And then B puts on the brakes. He stops. And then he turns around, reaccelerates to 0.6 speed of light, heads home, and in another 15 years, B heads home and arrives back at A, and the two brothers are back together. So this is actually hard as a thought experiment. What happens here is a big problem, because if you think about it, B traveling at 0.6 the speed of light suddenly stops, just zero, stops. What is B going to be? He's going to be a pile of blood on the front hull of his bloody spaceship. It's not going to be pretty. And in fact, to actually slow down from half the speed of light, 60% of the speed of light, it would actually take a couple months to do it safely. So, and I don't want to add a couple months to this thought problem. I want to keep it a super simple, super clean thought problem, no bloody astronauts. So I've introduced the tag team method. It avoids blood, keeps things clean. And what you do is you hypothesize a third person, a second traveler in a spaceship C that starts out at time 0. When B is just leaving A, this guy C is 18 light years away, and he's coming in at exactly the same speed, point C. So then 15 years later, C is arriving at 9 light years out at exactly the same time that B is arriving 15 years later. And so B and C actually could meet. And just like a wrestling match, B, who is the participant in this thought experiment, B could tag out to C and say, hey, as I pass by, you're it, C. And C becomes the personage, the traveler for the return trip. And so we have a clean transfer. B is going this way, and then all of a sudden, C's going that way. They tagged each other. They are basically the same. We have a single point in space-time when they touched, when they tagged. So C takes B's place, but very clean, no blood. And in exactly 30 years, C heads home, takes 15 years to get back to A. And so 15 years out, 15 years back, 30 years altogether. And that's in Space Station A's reference frame. So, and what is it going to look like to Space Station A? Well, he's going to see that brother head out for 24 years, and then he'll see the turnaround, and in 6 years, he'll zoom back, and the total will be 30 years. And here is the space-time diagram for that, very similar to the ones I showed you. If the space station happens to send out a pulse at 6 years, that pulse is going to bounce off B right when it's 9 light years out, right at the turnaround point, and it's not going to come back until time 24. And this is why I say the space station is going to see spaceship B receding for 24 years, and then from 24 to 30, in that 6-year interval, whoosh, B will rush back. And that's weird. I admit that's weird. So there's the 9 light year turnaround point. So here is the space-time diagram with the movie. At 6 years, that light beam bounces at, and then reaches the space station at 24, and the brother himself arrives at 30 years, 6 years later. So I've got a hypothetical, perfect telescope where you can watch your brother, one brother, the stay-at-home brother, can watch the other brother, and this telescope is magic. It multiplies. You can see your brother even if he's 15 light years away. So it's going to give a readout like this. You will have a time and a distance. And the tricky part here is the distance that's going to be displayed on our perfect telescope is the last inferred distance. So if I sent out a beam at 3 and it came back at 12, that's a distance of 9 years, so 4.5 light years away. And it happened 4.5 light years before at time 7.5. So when this spaceship is 4.5 light years away, even though my clock says 12 years, I know that actually this balance happened 4.5 years ago. I'm seeing the past. So that's how it's going to work. And here we go. Here is our journey. And we'll notice when this gets to 12 years, half of the 24-year journey outbound, it's going to show exactly half of the 9 light years out. We're coming up 12 years here, 4.5 light years there. Boom. And we keep going. And this ship keeps getting further away. The turnaround will be at 24 years. And we can see it's getting closer, only 4 years away, getting closer to 9 light years out. And 23 years, here we go, 9 light years at 24. And look, ooh, the brakes come on. Oh, now he's coming toward us. He's coming home. And here's where it gets fast. 26 years, 27 years, 4.5, 28 years, 29 years, and 30 years. He's home. And he said, long time no see, bro. 24 long years, eh? 24, it took me 30. So definitely the stay-at-home brother is 6 years older than the twin. Okay. So what does brother B, the traveling twin? Well, here is his space diagram, and it's not one single space diagram. It can't be, because twin B is basically going this way and then stops, turns around, changes reference frame. That is the big difference. And if we were having to slow down and turn around, the stress from deceleration and acceleration would be intense. The two brothers do not have identical experiences. And even in this super simple thought experiment, what's different is that twin B has to change reference frames, basically from twin B to twin C, and that's all the difference. So twin B goes out for 12 years and sees the spaceship 4.5 light years away. He turns around and comes back, and that takes another 12 years. So the brothers do not have identical. Here is B's movie. Here he's looking at Space Station A, and it's going to be exactly symmetrical up to a point. So when this gets to 12 years, it's going to be 4.5 light years, just like it was before. But now B turns around and he loses sync with the entire universe. The whole universe, he's lost it. He has no idea where that space station actually is. but he's heading back toward it. His clock is working. He's sending new light beams, new radar, and they finally balance off the space station. They finally get a reading 4.5 light years out, and then 3. And at 24 years, he arrives home at Space Station A. Long time no see, bro. 24 long years. So yes, brother, the stay-at-home space station, brother A, sees 24 years out, 6 years back. The twin sees 12 years out, 12 years back, 24 years total, 6 years faster than the 30. So now this movie shows what happens if Einstein was wrong. And as the spaceship is cruising away from us at 60% of the speed of light, the light from it is actually crawling towards us at 40% because it's the 100% of the speed of light minus the 60% going away. So we see, we passed 12 years, we're still not to 4.5 light years. And then about over 20 years, something really weird happens. Boom, here it is. There's 2 images, dual targets. Here's the space station still going out, but now we see the B on the return trip. This light is racing toward us at 160% of the speed of light. It's going to get here fast. 30 years. The twin returns. He's back home, and then both twins, the twin that was in the spaceship, can sit in the lab and look at the traveling ship for 7.5 years, because this is the slow light. And then it'll wink out at 37.5 years, target lost. Holy cow. So, and to me, that seems really strange. And yes, relativity is strange. Time dilation is strange. Length contraction, pretty odd. But what would be more odd, seeing those 37 stars going in a jewel train, seeing for a brother to be able to look at himself because he came back faster than those light rays. Whoa, that seems really strange. So, like I said, Maxwell's equations, when you solve for them, you get these electromagnetic waves, but the waves require changes in space and time. The del squared, those are changes in space. The d by d2 squared, those are changes in time, and they are interlocked. So if you were the Flash and you could catch up to a light wave and be going the speed of light, why, then you'd see this thing, but they wouldn't be changing. And you couldn't actually have a light wave because E and B, the electric and magnetic fields, would suddenly be constant, not changing, not creating electromagnetic waves, and the whole thing would fall apart. So the Flash can't catch up to a light wave. We can't go the speed of light. And no matter how fast we go, the speed of light's always going to be 299 million meters per second. It's the law, 670 million miles per hour. So that's all I had. We'll stop the share, and any thoughts? We do have a program for next month already, but I'm sure there's a couple questions. I have a question. What do you think are the odds that Dr. Hamdoon Khan will realize that I actually explained the twin paradox and send us the $20,000? Well, I'll give it an over under of 0, but we'll see. So yeah, I'll be able, when this comes out on YouTube, I'll be able to drop a comment on his video and say, hey, we talked about your video. All right, any further comments there? So next month, as I mentioned, we'll have a talk from a researcher down here at Tech, Mustafa Hassamanian, who has been doing really neat stuff with drones. And he's basically building drones that can fly with birds and imitate their motions. I've been telling the big feet people, you guys, need to look at what the Animal Planet is doing with these penguins, little robot penguins that live with flocks of penguins, and just make a robot animal that the Bigfoot would trust. Get it out there. When you get that video of the Bigfoot family 5 feet away, we'll believe you. We're ready. But yeah, just look at what the Animal Planet's doing. But anyway, that'll be next month. All right. Oh, and there is something else. So tomorrow night, and I thought I had this in that PowerPoint. Yeah, here we go. So let me screen share one more time. Okay, so tomorrow at 8:30 our time, one of our speakers from 2 months ago, John Hoops, a archaeologist at Kansas, University of Kansas, is going to be giving a talk on this ancient apocalypse film that was on Netflix, and the general lost civilizations. Basically, the claim that the ancient civilizations we know about, that wasn't it. There was a really advanced civilization before all that somehow disappeared. And so John Hoops will be talking about that tomorrow. So bit.ly. I did try it out, and the first part case doesn't matter. Second part, better use uppercase characters. BAS, Bay Area Skeptics, Hoop for John Hoops, and uppercase will get you right to the YouTube video. So tomorrow. Excellent. Glad I remembered to mention that. And okay. So any other comments? We have something in the chat. And oh, here we go. Thanks to Austin. Okay. All righty then. Well, we'll see you next month when we look at drones. And in the meantime, anybody wants to drop John a letter, now is probably a better time to do it than next month. So take care out there, and we'll see you later. All righty.